şey oldu hani
Bu bir dakikalikti. Bir dakika verecekler bunu ona. Bir dakika. Yeah.
Missing.
One.
Yours?
Missing.
Is it yours?
No. But Türkçe is not bir dakika.
Bir dakika, yes.
Bir dakika, yeah, bir dakika.
But we have to announce this one also.
That they are missing or
Missing.
they are, maybe they will place them or I don't know.
And the first one is Shadon. And you are after
Shadon.
you can invite. Then the
Okay.
second one I can invite.
Okay, great.
Third one, Gerhard, you can invite this one. Local assessment redemption. And the fourth one also maybe.
Which
Okay.
one is?
He is going to
He's
start
doing-
and
yeah.
invite this one, and I do this one, and you do this one.
Yeah, okay. The estimate of
By
level
the way,
size.
I now found that this is my brother. I
Yes,
didn't
it's
know
mine.
that he's a part of this topic.
Who?
Tahir Ismailzadeh.
I
He's
thought that it's you.
no, it's not me. It's my brother. I know Gulam, but he included him also. Probably he's seismologist dealing here.
If your brother means what? Really brother?
Yeah, exactly. He's my brother. I mean, it's no cousin, brother. But I didn't know that it's a brother will be a part of this.
But maybe he may know.
Yeah, no, he knows, but he didn't mention me. I asked today this
Have a look.
Gulam, yeah.
This is good.
Probably we have to start at already
Yeah.
9 o'clock. Good morning, everybody. Let's start our session of today. And this session is quite important really to look at the structure of the Earth and to see the how structure of the Earth help to monitor the in general, how it's scientifically valid and how it's scientifically important for CCBTO and how CCBTO can use the modern knowledge from seismology and the structure of the Earth. Well, the first talk will be given by the Chardon with co-authors, and the topic is a three-dimensional seismic velocity model of the Eastern Mediterranean region using body wave tomography. Yes, speakers here, 15 minutes, including question, please.
Maybe before my presentation.
We can tell it's a little bit late after that, maybe. How you wish.
It's for next. Yeah, but I want to go back. I'm just not going back. Okay. Good morning, everyone. My name is Louis Chardon. I'm a postdoc in Tel Aviv University. And today I'll be presenting our recent efforts towards building 3D seismic velocity model of the Eastern Mediterranean. And this is a collaboration between Tel Aviv University, where I'm based, and SOREC Nuclear Research Center. So I'll start my talk by an introduction on recent and also old seismic tomography studies of Israel. I'll then introduce the Israeli seismic bulletin that we've been using, and then I'll show you a test tomographic model that we have built, and finally I'll present the framework used at the CTBTO for tomographic studies, and I'll finish with some conclusions and outlook. The motivation behind this model of the Eastern Mediterranean was started after the recent developments in the earthquake early warning system that is being built in Israel, and whether the application is to warn of a potentially dangerous earthquake, or to differentiate between an earthquake and a possible explosion the precision of the seismic location is everything. The location depends on the theory and the technique used, but most of all, it depends on the velocity model. It was shown recently that the currently used model by the Israeli agency brings a lot of very large errors. So it's what you can see in the red frame, and that other 1D velocity models actually show much smaller errors. And all of those models are 1D, and obviously, though it has never been tested, we can imagine that a 3D model could also do a much better job. A little background on seismic tomography. It is a technique, an inversion technique to retrieve the physical properties of the Earth. The inputs are seismic data that we record at the surface. The forward problem equation allows us to predict travel times given a velocity model. The problem is most of the time nonlinear, which forces us to use iterative or probabilistic solving methods. And the problem is also underdetermined, which means that we need to use smoothing and damping operators. About local studies, local tomographic studies in Israel, there's been a number of local tomographies using local data recorded in and around Israel. I'm not going to go into details, but the general consensus is that the Dead Sea Fault and the Dead Sea Basin show very low velocities, which is limited to the crust. And so this is the case along the Dead Sea Fault, which is here. The Dead Sea Basin is here. We also see low velocities following the Carmel Fault zone that goes from the Dead Sea Fault to the Mediterranean. And at greater depth, there seems to be two high velocity anomalies on either side of the southern part of the Dead Sea Fault. As you can see, most studies are very local. Oops, sorry. Yes. There's only been one study that is at a greater scale, but the results are very similar to the local studies. So this larger study that I just mentioned used data from the ISC, which is a global database, and I'll mention later why it is a bit of a problem when we want to perform local seismic tomography. And what we used in our specific case is the Israeli local seismic bulletin. So the Israeli seismic bulletin is put together by the Geophysical Institute of Israel. It is responsible for monitoring a number of about 40 stations inside Israel, and the bulletin itself also collects data from neighboring countries. In terms of seismicity, the database started in the 80s, and it includes local, regional, and teleseismic events. And the big plus of this bulletin is that it also includes man-made seismicity, most of all quarry blasts, whether in Israel or in Jordan and other neighboring countries. So the problem in Israel, as you may know, is that the seismicity is very low. This map shows all earthquakes present in the database, so since the 80s, of magnitude 4 and higher. And as you can see, it's not a lot. But this is the data set that I'm using at the moment. You can see that um, oh, yes, all the colored dots are earthquakes, and the black dots are man-made explosions. The purple stars are calibration explosions, which are very important because we know exactly where they happened, and that's very useful when we try to relocate the whole catalog. On the right, I'm just showing all of the stations that are present in the database, and the frame represents the area shown on the left. And just to give you an idea, the previous slide showed 179 sources, which is basically what will be reported in global databases like the ISC, because of detectability issues and also signal-to-noise ratios. But in our database, we have 100,000 sources, about 100,000 earthquakes and 14,000 man-made explosions. No, the other way around. 14,000 earthquakes and 100,000 explosions. Okay, the next two figures are gonna show the geographical coverage of the data sets. To build this figure, I traced seismic rays using the TOPI software and the AK135 reference model. And I then gridded the area of interest every quarter of a degree and counted the number of seismic rays also as a function of depth. So each column, is for different depth. The first row is for PG phases and the second for PN phases. And basically you can see that the coverage is very good for PG close to the surface and decreases with depth but stays very large. Oh, really? Okay. The second figure shows you that PN coverage is good at the surface and at the MOHO where waves are refracted. I'm going to skip the second figure. So this model that's... What? Yes. So the test model that we've been running was using the fast matching tomography methods. It allows very different data types and also to include complex structures. For the test model, I built a grid every 5 kilometers in depth and every quarter of a degree laterally. And at the moment, I only invert for VP and keep the MOHO constant and don't do any event relocation. This is the results at different depths. I'm not going to go into any details, but basically we retrieve similar structures that is observed in previous studies with a very low velocity along the Dead Sea Fault and in the Dead Sea Basin. Those are cross sections. The ultimate idea is to build a model within the CTBTO framework. The current framework uses the regional seismic travel time software, which is also a regional model. It was initially designed to trace rays at regional scale, but also has all the tools necessary to build a tomographic model. The main issue is that currently the nodes are limited to 1 degree spacing, which is way too large for the local study in Israel. In conclusion, we have put together a very large data set that mainly includes, on top of global, as opposed to global databases, low magnitude sources, as well as man-made explosions, which gives us a greater source coverage. This data set is going to increase in size because currently they are still installing new stations for the earthquake early warning. As I briefly showed, the velocity model is in good agreement with the literature, although it is limited to PG data and it has no MOHO variations. And ultimately, we can increase the sensitivity in depth and and geographically using either other regional phases like PN, or also by combining it with other data like teleseismic data. Thank you.
Thank you very much. We have time for one, or if it's short, 2 questions. Please, auditorium. I have a question about the completeness of your catalog, because it's, you show that it's, that's a very rare events. We know that's rare events, but you use also these artificial, I mean, it's explosions.
Mm-hmm.
And then what is the completeness of this joint catalog?
In terms of magnitude?
Yes.
Around 1.5 magnitude.
Okay, very good. Any other question? No. Thank you very much.
I want to ask one question.
Yes, oh, sorry.
And I just want to know how you compile the data from ISC and also from Israel Bulletin in regards to the location difference and also residuals and the depth.
So we're not using the ISC database. I just mentioned it because it was used in another study.
Yes.
Just to use as a proof that using a local bulletin, not the ISC, has the advantage of including lower magnitudes, and in the case of the Israeli bulletin, also man-made explosions from quarries.
Okay.
But we are not using the ISC
Yeah. I just,
yet.
thank you.
Maybe we'll use it in
Yeah.
the future.
And hope you can use the teleseismic data and use also the CTPTO data, maybe, to understand from regionally recorded one,
Mm-hmm.
PN or SNSG.
Yes, the database is very large right now, so we're not going to add more, but yes, like ultimately we could also include more data, like the CTBTO data, the ISC data. Yes.
Okay, thank you. Okay, yeah. Second presentations named as earthquake swarms and reactivation of seismicity associated with the 2015 MW 7.8 magnitude Gorkha earthquake in Nepal. And presentator's name is Athi Kari, please. But before that, I would like to announce some posters are missing, and we kindly invite you to put your layout, your poster in the session set. It's more than 20 posters in this section are missing.
Thank you. Good morning, everybody. I'm going to present the earthquake swarm and reactivation of seismicity associated with 2015 Gorkha earthquake in Nepal. I'm working in National Seismological Center of Nepal. The content of my talk will be as shown in the slide. Just I want to briefly introduce the status of CTBTO in Nepal. Nepal has signed the CTBTO in fact 8th October 1996, but it has not ratified yet. CTBTO has proposed an auxiliary seismic station AS68 in Lobuche, which is shown in the red triangle, which is near the Mount Everest. And after the visit of Executive Secretary of CTBTO in 2001, it is cancelled just because of the not suitable place for the maintenance and other things. And afterward, 2 places, Phulchoki and Kokani, shown in the black triangle, were selected. So out of 2, the Kokani station is selected for the site, but till now, the station has not been installed. The Ministry of Education, Science and Technology is the focal point, and National Seismological Center of Department of Mines and Geology is the NDC, designed at the NDC in Nepal. Now I would like to proceed my talk. The MHT main Himalayan thrust is a plate boundary fault which separates Indian plate in the south to the Tibetan plateau in the north. Most of the interseismic seismicity or seismicity in Himalaya nucleates in the down deep section in of the logged portion of the main Himalayan thrust, which is fully logged along the Himalaya. During the large and great earthquake, it ruptured many times in the past. For example, it was ruptured partially during the Gorkha earthquake, 2015, along the 140 by 50 kilometer range of the MHT. Here we can see which ruptured about in maximum slip of 6 meter. The maximum slip was 6 meter. And the MHT was ruptured fully up to the surface during the 1934 earthquake, as shown in the figure. Many aftershocks were recorded just after the Gorkha earthquake in and around the ruptured area of the Gorkha earthquake. Some of the aftershocks and clusters were even recorded outside of the rupture area. This shows the 2 meter co-seismic slip of the Gorkha earthquake. So many, there are some clusters of aftershocks which are seen just after the Gorkha earthquake. That means there were no seismicity before the Gorkha earthquake in the last 20 years of seismicity monitoring in Nepal. The completeness magnitude of these clusters is below 2.5, except for the swarm, which locates outside of the rupture zone. And the B value is around 0.8, except even for the swarm. The behavior of seismicity is not similar if we look at these clusters. Like in Kathmandu, the capital city, this was the new developed swarm after the Gorkha earthquake, where there were no seismicity before the earthquake. And similarly, after 2 years of the Gorkha earthquake, the swarm is occurred in the vicinity of the rupture area. We can see in the behavior in the picture. I will talk briefly about the clusters that are odd to see. That means the one of the cluster that developed just after the Gorkha earthquake, Kathmandu cluster. This is still active with felt earthquake. The activity is decreasing. The maximum magnitude in this cluster was below 6. The magnitude of completeness is 2.3 in the cluster. And this cluster just locates the hypocenters in the mid-crustal depth, which was activated, the faults were activated during the Gorkha earthquake. If we look at the seismicity in the swarm, this shows the time, the date, and the magnitude for the black line, and in the red, so this is the cumulative number of earthquake in the swarm, which developed in 2017 in August, abruptly, about 2 years after the Gorkha earthquake, and that reoccurred in 2018 with less than 8 times of seismic activity. And the maximum magnitude of this swarm was less than 4 local magnitude. And more than 7,000 events were recorded during these 2 periods in the area. The Himalchuli swarm, the maximum magnitude of completeness is, the completeness magnitude is about 3 using the maximum likelihood method, and the B value is greater than 2.2, which is totally different from what we observed in other clusters. The cumulative moment increases almost constantly, which is different from the main shock and aftershock crisis. And similarly, the B value is very different from others. If the cumulative moment released, dissipated, is equivalent to the magnitude 5 earthquake. In this figure, this is the location of the swarm using the permanent seismic network, which lies south of the swarm. Due to the poor coverage of azimuthal coverage, there is large uncertainty in the location and the depth, as we can see. And by using a temporary station data just north of the swamp, so we see the location of the swamp is totally lies in the south of the high mountains, these two 8,000 meter high mountain and the Himalchali mountain in front of these mountains. And the relocation of these events entirely shows all events in the hanging wall of the MHT. In blue, this is the seasonal geodetic seasonal data, displacement data near to the swamp, and these are the magnitude and the time for the swamp. And when, as we know, the seasonal variation due to the flexure in the Indian plate is in the area. So we calculate the stress, the Coulomb stress in the plane, which I showed in before, and we see the seasonal variation in the stress when we calculated it in the plane. So this is a model that I proposed. This work is still going on. During the co-seismic slip, there was extension, there was subsidence, and at the same time there was after slip, the co-seismic slip and after slip. And at that time, maybe this area is broken due to the different forces, and just it was clamped just because of the after slip and the flexure in the Indian plate. And after 2 years, with less after slip and less seasonal signals, it is maybe broken, and the swamp occurred in the region. And so this is the plane that we can see here. And this year in 2019, so there are no seismicity associated, we don't see. So in general, just to show, so this belongs to this is the cumulative curve, but this second peak belongs to the swamp, not for any large event. And still the aftershocks of Gorkha earthquake are there. The rate of earthquake are more than 6 times compared to before the Gorkha earthquake in the rupture area. I want to conclude my talk with the following conclusion. The rate of earthquake is still 6 times more, and lateral variation are related to the structural depth at the depth in the many-valent thrust. And a large swamp developed outside of the rupture zone in 2017 and again in 2018. Probably this swamp is related to the collapse of the Himalchali, the mountain, and triggered after the first period of the deep after slip. Thank you, and just this figure is to show the swamp occurred in front of this mountain here, in this area. Thank you.
Thank you very much. Nepal is very interesting country in geographically, tectonically, and also seismically. It's very worthy study. I'm opening the floor for question. Are there any? Yes, please.
Yeah, please take a microphone.
Do you have some
Focal mechanism
available to support your theory?
This is the thing I'm lacking, and it is very difficult to have a focal mechanism from the event that I have, because all the events are less than 3.5 local magnitude. That corresponds to less than 3 moment magnitude. So till now I don't have, but so still I'm trying to work on it, but the area already lies in the normal faulting edge zone. So,
okay.
And we don't have any focal mechanism in that area just to show any kind of focal mechanism, yeah. But the area lies in the previous study, not by the focal mechanism, that just by the general study, and in the Tibetan plate and in the southern part. Yeah. So this area lies in the normal mechanism area. Yeah.
Okay, thank you.
I think there are some new tools, new programs which can go down to the magnitude 3 also to determine the focal mechanism. It would be really worthy if you solve the focal mechanism solution to understand all the defaulting, dipping, and the geometry of the tectonics. That would be good. Are there any other questions? Thank you very much.
Welcome.
So with that, we will be moving on to the third presentation this morning. This is on the estimation of local seismic activity by deterministic hazard assessment, a case study in northeastern Azerbaijan. And this will be given by Babayev.
Good morning, everyone. First of all, thank you very much for this opportunity that I received in participating in this conference. So, the title of my talk is the Estimation of Local Seismic Activity by Deterministic Hazard Assessment, a case study which is applied for northeastern of Azerbaijan. We have a bunch of authors of this research. And next, the aim of this research was to assess seismic hazard the southern slope of the Greater Caucasus in Azerbaijan on the basis of deterministic theory with integrated combination of several approaches. The main objective of the paper of this research is to carry out seismic hazard analysis on a quantitatively estimation and empirically to define the expected hazard in the southern slope of the Greater Caucasus. In this study, we perform a strong motion simulation in the values of peak ground acceleration for the southern slope of the Greater Caucasus from the integrated analysis of seismic engineering geology, effects of soil and rock to seismic wave amplification factor. We also considered attenuation characteristics and side response. Mountains of the Greater Caucasus extend between Black Sea and Caspian Sea. In our study, we concentrated on these three zones, which is mentioned by 1, 2, 3 respectively, the Balakan Zakatala, Sheki Gabala, and Ismaili Shamakh zones, respectively, 1, 2, 3. Those are seismically active zones in Azerbaijan, one of the seismic active zones, in fact. Study area is situated in the active continent collision of the Arabian-Eurasian plates and involved in dynamics of the lithospheric structural units of those plates, as you can see. The Greater Caucasus is wholly situated in an interplate setting within the Eurasian plate. Southern slope of the Greater Caucasus is characterized by mountain ranges with an average of elevation of about 4,466 meters. In this map, we can see red color, which indicate the shallow earthquakes, the existence of shallow earthquakes, and blue color is deep earthquakes. Concerning focal mechanism solutions for the period 2003-2018 for the earthquake with magnitude more than 3, you can see in this map the distribution of focal mechanism around or throughout those 3 zones. Balakan Zakatala zone, Sheki Gabala zone, and Shamakh Ismaili zone. Balakan-Zakatala zone is characterized by the extension, and the displacements of those areas are mainly normal deep sleeps and normal faults with strike slip component motion. The Sheki-Ismaili zone throughout is characterized mostly by compression with the thrust and reverse fault types. Concerning distribution of earthquake epicenters between 2012-2018, you can see from this map, again, it's a repetition. First is the Balakan-Zakatala, second zone Sheki-Gabala, and third one is the Ismaili-Shamakh. The analysis of the earthquake distribution demonstrates that most of the strong earthquakes with magnitudes more than equal 5 are confined within crystalline basement. Mainly Zakatala and Shamakh areas are distinguished by high seismicity, by high seismic activity, high density of seismic events. These areas are characterized by magnitude range of 3.4, 5.9. Sheki area is relatively distinguished by low activity with magnitude range of 3.1, 3.4. During 2003-2018, about 8% of earthquakes, which around 235 events, occurred at the depths of 10 kilometers. Those are magnitude, local magnitude of more than 3.5 or equal. As we know, PGAP ground acceleration is the most widely used parameter to describe the shaking amplitude related to a seismic event, and for determining components of horizontal and vertical motions. Different methods exist to compute the PGA. PGA is estimated with attenuation laws. These relate magnitude and distance of an event with acceleration. PGA versus intensity scale with MSCHI of 64. This uses the intensity acceleration relationship. And PGA value is calculated with a methodology which depends on the type of data available. In this study, we concentrated on macroseismic data of the target earthquakes. We picked up some target earthquakes concerning magnitude, depth, epicentral distance, hypercentral distance. We also considered lithological factor, VP versus VS, and amplification factor as well. Concerning lithology and stratigraphy, in this study area, we encounter mostly with loamy hard sandstones, limestones, with shale and clays, with Jurassic up to Pliocene age. This is just an overview. We also combined some table which characterize the area in terms of age, geological age, in terms of lithology, in terms of the value of VP and VS, density, and amplification factor. We considered all these parameters in our study. We calculated depending on the formulas and approaches. In order to start the deterministic seismic hazard assessment approach, we used seismic scenario method. From this geological map, you can see our study area. We made a mesh of those study area. The base map of the study area is a geological map of Azerbaijan. You can see we divided the area of study into small meshes. The approach is a simple, just simplified approach, considering the formulas for estimation of the expected values of the maximum amplitudes, considering magnitude of the event, hypercentral distance, and this kind of rough sketch in our study area. Totally, for our study area, we have 46 cells of the study area. The distribution of earthquake within study area looks like that. As you can see, this area and this area is most dense. in terms of earthquake distribution. We calculated average earthquake magnitude estimation for various sources like fault pattern. For that, we use several fault maps, as you can see, and as a result, we have these magnitude distribution map concerning the availability of active faults using the empirical relationship between the length, rupture length, and magnitude of the event. And the maximum magnitude of 8 is estimated for the western area zone and is used to generate one of the seismic scenarios of the region. Here in this slide, we demonstrate the PGA distribution for the 4 earthquake scenarios. This one is for Ganja earthquake, which occurred in 1139. This is a component of that earthquake with magnitude 6.8 and focal depth 15. We have this kind of pattern of peak ground acceleration distribution. This one is the Schumacher earthquake, which occurred in 1902 with magnitude 6.9 and focal depth 15 kilometers. We have this kind of pattern of peak ground acceleration distribution. This one, the August earthquake, you can see, which occurred in 2015 with magnitude 5.9 and 13 kilometers with focal depth. We have this kind of pattern of peak ground acceleration distribution. And the last one is 2018 Zacatala earthquake. This is the epicenter, and with magnitude 5.5 and focal depth 10 kilometers. From these PGA maps, we see that the very high PGA is scattered in the west and east part of the study area. Independently from the epicenters of target earthquakes, the low and the very low PGA is scattered in the central part of the study area. This is the intensity and amplification map, as you can see. We arrived to the intensity map from the correlation between PGA and MSK 64. An amplification map was calculated using the formulas for hard rock cells and shake if we have soft rock in our cells. As a conclusion, a few points which need to be considered and taken in mind. Demonstrated that ground displacements are various and not obviously oriented towards seismic source. Seismic intensity increase is observed in the areas with soft cemented sandstone, clay deposits, although there are some inclinations of sandstone, limestone, and sandy marl in them with various thicknesses. These areas are characterized by high values of amplification factor. Those are areas with sharp decrease of PGA values, which is explained most probably due to the interlink with the damping factor of the study area. Thank you very much for your attention.
Thank you very much. I will open the floor for a couple of questions, please, at the back. The lady in red, yes?
Lady in red, yes.
Yes, you.
Microphone is just next to you.
I was wondering, there are a bunch of earthquakes in that region, very strong earthquakes. Did you compare that earthquakes PGA values with your deterministic results?
In fact, we selected 4 target earthquakes considering the distance, the magnitude level, and the effect in terms of intensity. We used the historical earthquakes, which occurred in 1139 and 1902, and those are one of the strong earthquakes recorded in Azerbaijan.
Can I ask a question, maybe the similar one? I also wonder how you estimate the value of PGA for the earthquake 19.2.
1902.
Yes.
Considering the magnitude, in fact, the sketch is to define the PGA at bedrock, considering bedrock, and then when we have the PGA bedrock using the formulas with magnitude parameter and hypercentral distance, and then we consider the amplification factor for each layer, and the surface PGA is calculated knowing PGA bedrock, bedrock PGA, and amplification factor of each layer.
Okay, thank you.
Yes, please.
Yeah, thank you for your presentation. And now from your PGA maps, there seems to be a clear reversal of the PGA values from shallow, intermediate, and deeper levels. Any explanation on the basis of geology?
In fact, not from geology, but from the lithological factor. There are several layers and deposits when we have attenuation factor in line with amplification. So there are some uncertainties in terms of lithology in that area. And tectonical factor as well, like faulting and, of course, the lithology.
Thank you very much. We need to move on to the next presentation. If you have any other questions, please use the app, or there's also time, I'm sure, over another cup of coffee. Thank you.
Thank you. Thank you.
Okay, so it's my pleasure to invite the next speaker to come up. A paper by Perry, McNamara, Myers, Begnot, and McCormack from Canada and the United States.
Okay, good morning. My name is Claire Perry, and I'm with the Canadian Hazards Information Service in Ottawa, Canada, at the Canadian Data Centre. And today I'll be discussing some of the methods that we are currently using to improve knowledge of crustal structure, and of course its implications on seismic waveform propagation and seismic energy dissipation. So I'll be focusing on two specific studies. The first one is LG amplitudes and looking at regional QF studies in different regions of Canada. So this is attenuation on a regional scale. The second study will be looking at travel times and improving towards improving event location accuracy within Canada. And this will be using the RSTT software and tomographic inversion to extend the model into Canada. So first off, we're using a well-established method to determine frequency-dependent attenuation, that is the reciprocal of Q, the quality factor, within multiple regions across Canada, East and Arctic specifically. We'll be presenting in this talk. So basically we're using input displacement amplitudes and inverting for source, receiver term, and also the Q value, assuming standard values of geometrical spreading at regional distances. So this will give you an idea of how the displacement amplitudes are calculated. You see in the blue is the LG velocity window compared to the S-coda window in red. And we look at the RMS amplitudes in the LG window compared to the S-coda window, determine whether the waveform passes the signal-to-noise criteria. This event was recorded in the Grenville province of Eastern Canada. So here to summarize the regions that we've currently studied within Canada. The first is shown here in red, the eastern Canada, including the Grenville province to the north of the St. Lawrence River, and the Appalachian province, northern Appalachian province, as well as the Arctic region here in this circular zone, and a seismically active Boothia-Ungava region within that Arctic zone. Here you see the ray paths, LG ray paths between source and receivers for Boothia-Ungava, Canadian Arctic, and also within the northern Appalachians and Grenville provinces. So here it is an example of the LG amplitudes as a function of epicentral distance, depending on the frequency band, narrow frequency band filtered for. The black triangles represent raw amplitudes, and the red dots represent the source and receiver term corrected amplitudes coming out of the inversion. And again, the slope, basically the best fit slope, the best fit slope of that red line represents the Q value at each frequency band. This is for the Grenville province as an example. We also carried out random data reduction inversion analysis, jackknife inversion, where we removed a random number of data and got a measure of the standard deviation of our Q values to put some kind of error bounds on our estimates. So in each inversion, we check out the source term and receiver terms and make sure that they're sensible, that the source term increases with increasing source magnitude as well as decreasing frequency, and that the receiver terms follow what we see geologically, and that if we have increased sediment thickness, we would expect a higher amplification factor. So here, to summarize, we're looking at differences in attenuation, in apparent frequency-dependent attenuation between the Grenville and Northern Appalachian provinces. And what's important here is that we see that the Northern Appalachian province seems to be much more highly attenuating than does the Grenville province. Again, attenuation is the reciprocal of Q, the quality factor. And these differences between geological provinces in Q or seismic attenuation are important in the calculation of regional magnitudes and comparing magnitudes between regions. For the Arctic region, we see a high Q value across the general large-scale Arctic. However, the Boothia-Ungava zone, which was a tectonically active zone in the Cenozoic and home to rifting at that time, shows a much lower Q value. And so we have to be very careful about magnitude estimates and comparing magnitudes then between regions where ray paths may cross multiple regions of different seismic attenuation and energy dissipation. So here's an example where we took an independent seismic data set of events occurring within the St. Lawrence River between the Grenville and Appalachian province, magnitude 2 and above. And we recalculated MBLG magnitudes for these events using the attenuation relations established here. And what we found is that looking at the difference between MBLG and the Northern Appalachians and Grenville, we're able to reduce the residual magnitude between the regions to basically zero using regionally appropriate attenuation relations as compared to a constant value of 1400 Q, which leaves a residual of 0.13 between Appalachian and Grenville. So this has important applications for looking at magnitudes, again, across regions, and also considering ray paths that traverse multiple provinces. The second project that I've been working on is extending the RSTT regional seismic travel time software and tomography into Canada. So in the RSTT model, wave speed is calculated through tomography such that wave speeds are optimized for the observed minus predicted travel times to be minimized. Velocity profiles are assigned to start at each tessellation grid and then adjusted. We use the CRUST 1.0 model as a starting point, and we are looking for travel times of regional and local phases, PG, LG, PN, and SN. So we're using both seismic, natural, and anthropogenic events going into this RSTT Canada model. So Mike Bonneau in his talk following mine will give some more information regarding the tomography overview, but basically we're starting with the RSTT 2014-04 UM model, and then inputting our NEDB Canadian database data set of earthquakes, rock bursts, blasts, and explosions. Then we relocate these events using the Bayes-Lock routine of Myers, and then solve for upper mantle slowness, upper mantle gradient, as well as crustal velocities, PG and LG, or slowness, if you will. And it's important to note that the assumption of the regional and local phases is head waves, so the PG and LG waves will propagate along the mid-crust interface, whereas the PN and SN dive into the mantle, and we've taken into account the diving ray term, the gamma, in the tomography. Again, Mike will give more detail on this in just a minute. So here are the input data sets into RSTT Canada. So we have natural earthquakes, GT0 mining events, where these are mining events that have been confirmed in terms of time, depth, and location by mining operators. We also have GT5 and above mining events, GT0 refraction explosions from the lithoprobe experiment, as well as blasts occurring across the country. GT levels are defined by the Bondar criteria from Bondar and others, 2004. So here's the Canada model, input model of additional data that's going into the RSTT. Here we have the crustal velocities PG and LG, and PN and SN. These are ray density plots. And we can look at this another way. We can actually see the ray path coverage of PG and LG crustal rays and PN and SN mantle phases. So we have good coverage across the country, including in the Arctic. We tested Bayes-Lock performance, and it seems to be doing very well for the Charlevoix seismic zone in eastern Canada, as well as the Vancouver Island region and the Great Lakes Basin. Here I show the reduced travel time as a function of distance in all of the regions, and the reducing velocity is shown in the inside of each figure. The open blue circles are the input PG, observed PG velocities. Open red circles are observed PN velocities. And the Bayes-Lock relocated travel times are shown in solid blue and red. So it does a great job of relocating these events and reducing the residuals and misfit along the travel times. What we see especially is in the Charlevoix seismic zone, 3 distinct bands of seismicity which we know exist, and Bayes-Lock does a great job of picking this up. Okay, so here is our starting model for the crustal velocities, for the crustal travel times. Here we get the PG crustal velocity and PN, PG crustal velocity and PN mantle velocity in kilometers per second, as well as the PN gradient. So again, this is the RSTT starting model. Once we add the Canadian data set into this, after 4 iterations, we end up with these maps. So here, PG crustal velocity in kilometers per second, PN velocity. We see a lot more detail in terms of in the craton, in the PN velocity, and also in the PG. We see more detail in the northwest of the Cordillera, as well as quite high PG velocities indicated in the Vancouver Island region and the St. Lawrence River rift zone. PN gradient basically changes in that the gradient becomes less and smaller within the craton region. So the starting S model, LG crustal velocity, SN velocity in kilometers per second, and SN gradient. We'll add the Canadian data set and iterate after 5 iterations. Here's our resulting S model, S-wave model, LG crustal velocity, SN velocity, and SN gradient. So we see much more detail in terms of LG velocity across all of Canada, actually, and especially in the north. And LG velocities are significantly lower here than they were with the starting model. SN velocities are also lower and show more detail across Canada. Again, the SN gradient is smaller compared to the original RSTT starting model. So to summarize, PNS travel time residuals for RSTT Canada, basically we see a reduction in local and regional residuals by combining the Canadian data set with the existing RSTD North America. So our starting model travel time residuals are here for the local and regional phases. Final model, we see a reduction of 17 to 50% in our travel time residuals with the new model. So to conclude, regionally appropriate attenuation relations should be applied when comparing magnitudes between regions. This is to ensure consistency between provinces and especially accuracy of seismic catalogs. One of the next steps will be to benchmark for ray paths traversing multiple regions on a larger scale attenuation model that's currently under development in Canada. Secondly, incorporation of the NEDB Canadian catalog into RSTT North America reduces travel time residuals quite significantly for both regional and local phases, with the biggest improvement showing on the LG phase, 50% reduction in travel times residuals. So the next step is assessment of event location accuracy with the updated RSTT Canada model, as well as development of a unified tomographic model for North America, which includes Canadian data sets and uses the regional frequency-dependent attenuation results to benchmark and validate the model. Thank you.
So thank you. And the LG work that you've done in this vast country, do you find any indication of any type of LG blockage from Hudson's Bay or anything like that? You did the variation of LG attenuation, but the concept in some countries of an actual blockage does not seem to be present anywhere in this vast country. So that's wonderful.
It is. It's very, yes, it's quite useful in terms of attenuation modeling. We do see some blockage in parts of the Arctic up here, Banks Island in this area. Mm-hmm. So this is the Arctic platform where we do see some crustal thinning. However, overall the crust is quite thick, but any type of significant variation in that crustal thickness can block the LG.
One reason for my question is a personal conviction that the LG phase is enabling highly precise event locations in another way to do this. It's wonderful to get this indication of regional waves of the strength that you've shown. So do we have time for any more questions, perhaps? Maybe a question, one. So perhaps we should, thank you.
Thank you.
Thank you. We'll move on. Thank you.
The next presentation is the updates to the, again, RSTT regional seismic travel time tomography model. Is Mr. Bagnaut.
Thank you. So yes, I'm from Los Alamos National Laboratory in the United States, and so I'm going to present results from our recent update of the RSTT tomography model. I want to acknowledge my co-authors, Steve Myers from Lawrence Livermore National Laboratory and Brian Young from Sandia National Laboratories. This is over a decade-long project where we're updating this model for different aspects of the use, and so this is our latest results. So the current status of the model and effort, the latest version release is, like Claire said, the 2014 version. It is available on the sandia.gov website /RSTT, including all the software that can interrogate the model, pulled out travel times and such, and functions for doing tomography. Significant advancements since that model update was we changed the crust and had additions and modifications of data from recent RSTT outreach workshops. Steve Myers' poster, which actually came down yesterday, but maybe it'll be available online. We have updated the crust from 2.0 to 1.0. We used a new data set using the BASIL program, which is a joint relative relocation program. The URL is listed there to improve event locations and accuracy. We also added a method for estimating path-specific travel time uncertainty based on the decomposition of residuals into uncertainty components. And we've begun modification of the public version of the travel time code to enable this uncertainty calculation. Hopefully that should be available on the website in the next few months. So this presentation is going to focus on an overview of the tomography, update to the new data set of all the tomography, so I'm going to be showing several images, overview of the uncertainty method, the calculation of the error components, and some preliminary validation of that. There's a lot more validation to be done, but I'll show some correction surfaces and travel time uncertainty surfaces. So like this same figure from Claire's talk previously, so RSTT we did recently was a multi-step process. We first tried to match the deep seismic sounding lines with the peaceful nuclear explosion data. We then added in the new baselock data. We set a constant gradient value as a starting model. It seems to behave better that way. Our inversion uses the standard LSQR algorithm, and we included regularization, which was optimized for the smoothing and the damping. So we're solving for the upper mantle slowness in the red. So here's the equation for that. For the travel time, for the upper mantle gradient, which is the c-squared parameter or the gamma parameter here, which involves the head wave distance as well as a constant in there, and the c is related to the upper mantle gradient and a correction for the radius of the Earth at the point. And we assume that this c value times the assumed bottoming depth of the ray is much less than 1. We're also solving for the PG and the LG crust. This is this portion of the equation and the graphical view of it here. And we're also solving for a crustal stack modifier that can be affected by the upgoing and downgoing legs of the ray path in the crust. So here's some view of the tomography for the PN and PG phases. For PN, the weighted residual root mean squared, by pick error, we had 1.9 million rays. We started at 1.42 seconds and finished at about 1.24. The lower improvement that we might see is because the starting model did a pretty good fit at the beginning from previous tomography. This is just a zoom in of the upper mantle velocity. What you'll see is areas that are dimmed. Those areas did not have any ray coverage, but I wanted to show them anyway. So they're reduced in intensity here. But you're seeing some of the results from the change in the starting model to crust 1.0, but then additions and adjustments from different tectonic areas, especially, are the most notable. Going into the upper mantle gradient, we have left that a little more muted, but with some of the features you see in the Western United States and into Europe and into Japan especially, where the subduction zone effect is clearly seen. And so for the PG side, the RMS value went from 1.59 to 0.83. We had about 410,000 rays. And in a zoom in of that, you see some of the structural features of the PG aspect of it, where we see some complicated features in the United States, mainly from the US array. into Europe and parts of Asia and in Japan. So these are some examples of correction surfaces that would be calculated for the PN phase. This is at 10 kilometers depth. This is relative to the ISB 91 velocity model. And you can see some of the patterns here. The rings are at 15, 18, and then 20 degrees, just to show some features of what is coming difference from the one-dimensional velocity model. I'm not going to describe those in depth. You can see those for yourself here. PG travel time, of course, because the PG is a little more variable, and based on the ISB, which is more of a group velocity, there's a little more extreme correction values here out to 10 plus or minus 10 seconds. BDFB in South America, there's less structure in the, less data in the model, so it's get a little more muted for the variations in the structure there. So moving on to the SN and LG. For SN, we have about 262,000 rays, going from about 4 seconds to 2 seconds for residual. Zooming in here, you can see a lot of the structure in the SN velocity. Again, dimmed areas where there's no ray coverage, which is basically the starting model. Upper mantle gradient also has some features that are observable. Western United States there and into the subduction zones. Usually anything with complex tectonics, especially subduction zones, will have a distinct feature here. For the LG, we had about 120,000 rays moving from about 2 seconds to 1.7 seconds. Here's some of the structure there. Yes, we have most of the data in the US and Eurasia, and that's what some of our outreach efforts and the workshops are trying to pull in data from the Southern Hemisphere, especially getting new data points, but that's a continued effort. This is some examples for the same stations for the SN travel time correction surfaces. Seeing some of the structure here. This color scale is more heavily weighted to the negative aspect of it, just based on the data and how it corrects from the 1D model. LG correction surfaces, same color scale. You'll see more variations closer in and less variation at farther distances. And so moving into the path-dependent uncertainty overview, I apologize, this is a very busy graph. This kind of lends itself to an entire talk. But so the goal for RSTT is for the general user to be able to estimate a path-dependent uncertainty now on the fly, like in the NDC in a box. And so we're using variations in apparent slowness residuals among model nodes to allow for separation into model, random or pick error, and bias components, and we use a random effects model to do this. We had several previous presentations at the CTBTO Working Group B Waveform Experts Group meetings. But for also areas with no ray coverage, we need to fill in with a value, so we use a background value. So in each of the distance bins, we produce from 2 to 16 degrees. We use a mean plus 2 standard deviations. And then we're also using a crustal component for the error estimates, which is roughly 18% of the weighted average slowness. So we're going to calculate a travel time uncertainty prediction for a specific path with nodes in the model that are touched, so the number like M, and so you would produce a M by M a mini covariance matrix of model and bias error values. The random error part of that is an optional component that's not usually used. So the total uncertainty would be the path weights multiplied by this covariance matrix, and then include the crustal aspects of the error. And so below on the bottom is a graphical cartoon of the ray paths where the nodes are touched here. You get an observed apparent slowness, a calculated apparent slowness, you get an apparent slowness residual. They're collected at each of the nodes in the model, and then we run a random effects model on that, and we produce different services. This is for the 6-degree distance bin, which this is the model error on the top, and then the bias component on the bottom. And then you have a different grid there for each distance bin. Next, I'm going to show some uncertainty surfaces for station phase, and just to try to illustrate how that's produced, you first determine a distance. For example, in this plot is for 8.65 degrees, so I would use the 8-degree distance bin For the model error or bias, the 10 degree, I would do an interpolation to produce one grid. Then I would use that grid to calculate build the covariance matrix for the specific ray path, and then to estimate an uncertainty. So the next step is for this, is I would do this in a grid. I produce different, this is a cartoon, of course. You're going to get a smoother value for interpolation. But this is to explain that you might get some ring-like structures depending on the model and bias errors. And you build this together. You're going to get one value for the travel time uncertainty for any specific ray, and they're going to be smooth as you move to different parts of the grid. So this is just an example of how that might work. This is an example for PN, for travel time uncertainty services. You will see there is a strong component on crustal thickness to this. The thicker the crust, the more component of the crustal error is going to be incorporated. But you'll see for Pinedale and GERES and CMAR, you see the crustal components. BDFB is not as much data down there, so you're going to see mostly a constant kind of value depending. This has got a crustal component to it. For PG, it's a little more extreme. I apologize, it looks like there's a gridding issue with this part with the strange feature here. But you can see that the structure varies on a 2D sense, or if there's not as much data, it looks a little more like a 1D. For SN, we see similar structures. There's also going to be a larger component of the crustal thickness to this. And the LG, we see structures in various areas, so we're getting path-dependent uncertainty estimates depending on where the station and the path are. So our conclusions and future work, we're completing a full model update for this. Using the Bazelak process global data set. We're doing preliminary validation at the moment. We're calculating error components for each phase using a random effects model. We're using 2-degree bins for this, and we get preliminary estimations and validation of this. And so we're working right now with Sandia National Laboratories on an update to the code to handle this 2D uncertainty, which we hope is available soon. And so some future validation work will include full validation for the IMS primary and auxiliary stations for travel time corrections and uncertainty. And then we'll do location tests with the uncertainty in the model just to see how they do for different phases. And then also possibly assisting with the development of source-specific station corrections for use by the IMS. Thank you.
Thank you. Floor is open for the questions. Are there any?
I have a question.
Yes, please.
I have a question. Thank you very much for a quite interesting talk. At the beginning, you mentioned about the regularization, and that is you optimize your regularization parameters, I understand, to new data. Because it's normally, my question is related, it's how much this optimization will influence your model. Actually, each time when you change the regularization parameter, you will get a new model.
Well, yes.
And it's how it's, because data always it's coming more and more data. It is not something
Right.
where
So an area with much more data should overcome some of the regularization parameters if there's enough data, but it's in case many areas have less data, and so we don't want it to be like the salt and pepper look or whatever you want to get to that, and be significant and smooth. Particularly for a velocity model that's using for location, the smoothness will help a little bit, so you may not get as refined features in some areas, but the smoother travel time predictions, less instability in the location. But we will do the optimization where looking at different smoothing and damping parameters and relative to the length scale of the model, and try to find using L curves and things like that. And so we'll find the optimal value. So yes, tomography, you change things. There's a little bit of an art to it, but usually with the L curve and other optimizations, you can get a good value and a stable value.
Yes, that's important. Thank you.
So at one point you had a reference to an LG ray, and I wasn't sure what that meant.
Well, we have to make some assumption. So for the LG and the PG component, we are doing this mid-crustal kind of a head wave assumption for calculating the travel time. So we have a layer in the mid-crust that is strictly for the LG or the PG. for those velocities specifically. So we have to estimate a travel time in some way, and that's the assumption we're using for this.
Yeah, thank you very much.
Thank you very much. Yes, our last point of this session is a poster review, and we know that 2 posters are, presentations are uploaded. Maybe it's more. And please, those who upload their presentation, come closer here, because it's, as you know, it's 1 minute allowed. And you are first, yeah? You have this, okay. Please give them to these ladies.
We can only preview what we have. We give you a list of numbers, I believe. And this is what we have through the system. It has to be controlled. Do you have the list of numbers, madam? I think
This one, yes.
these are the ones that we have. If you would please announce these numbers, you have to be standing in here in the right order. It's 1 minute per presenter.
They already upload there.
They have it has got to be pre-done.
Pre-done, okay. Thank you. Now we got a little bit different information.
Yes.
There are a number of the posters which is preloaded. As I understand, yeah, it's in advance. I will call the number by poster number, and please then it's approach the microphone here at the podium. P12 first. Poster P12. That's correct numbers which you gave?
These are the numbers that we have their posters. If you just read all the numbers so people could count.
Okay, well, then P13, if you will hear your number, please approach. P17, yes, well, first. P22, P30, P37. If you are here, please come closer here to the first row, yes. P51, P53, now I will tell without P. 58, please come closer here. It's the first row, please see. It's just not to disturb others here. 71, well, 73, very well, 80, 88, 102, 120, 122, 123, and 124. That's all numbers which we received. If somebody uploaded, but it's not in this list, anyway, please approach our assistant here. Thank you. You will call it. Okay.
Please, if you hear your number, approach the podium. P12, P13.
Oh, it is not working very well. Here should be an animated picture. Open it directly in Adobe Acrobat.
Yeah, I need to. Yeah, There's the Escher, I think.
Not in
No, I mean, this is
PPT,
Escher.
but in Adobe Acrobat.
You know, famous, there is the Austrian painter. Yeah.
It's PDF, and if you open it...
But could you just present your idea?
Oh, it's based on the animation.
But animation always problematic.
Okay. Ladies and gentlemen, my name is Martin Bednarek, and I would like to present an interesting feature which presents a challenge in future research. So in linear viscoelasticity, seismic wave velocities and the corresponding quality factors have to match each other, and not just for a single omega, but over the whole frequency range. And a mismatch could mean a thing which is physically, which might be physically interesting. We expect the Earth as a whole to be roughly viscoelastically consistent. So are we able to find some black sheep among the mating birds of quality factors and velocities? That's my question, and that's the challenge for the future research. Thank you very much.
B17, B22, 30, B37.
You are 30?
37. 30.
Good morning, ladies and gentlemen. My name is Tarzan Kwadiba. I'm from the Botswana Geoscience Institute, initially called Department of Geological Surveying. My work is on the use of P-wave tomography to explore the anatomy of the continental lithosphere beneath Southern Africa. Much of Southern Africa is underlain by the Kalahari Craton that comprises the Achaean, Cap Valley, and Zimbabwe Craton. Seismic tomography is one of the most fascinating subjects in modern seismology, and as it promises to answer a number of questions relating to the evolution and structure of continental land masses on Earth. Thank you.
Okay, so the detection of seismic events depends on a good understanding of heterogeneities and seismic anisotropy. But seismic anisotropy, especially like in shear wave splitting measurements, we have some depth problem. And here on my poster, I would like to show you a new approach to come over these problems, introducing the non-vertical shear wave splitting approach. So taking advantage of this incidence angle, we can distinguish between an asthenospheric and a lithospheric source of anisotropy, because there is a shift in the back azimuthal distribution of the fast orientation. This assumption, or this approach, we tested it in the data set for Western and Central US with more than 16,000 measurements at 1,700 stations. And I will show you if these derived variations are similar to the ones we expected from theory. And if you are interested in this, then come to my poster about the flow plane orientation in the upper band below the US, and we will find out if it's related to a simple asthenospheric flow or vertical current deformation. Thanks.
P51, P53, P58,
Okay, my name is, I'm Naomi Takahashi of the NIED Jamstech from Japan. I introduced the monitoring of cluster activity using ocean floor network system for disaster resilience. So NIED, one of the Japanese research institute, manages many types of the monitoring network system for earthquake, tsunami, and the volcanic activities. So here, we focus on the real-time data utilization obtained from ocean floor network system. So the very important points are two. One is the real-time prediction system. We already constructed the real-time time prediction system, and now we are implementing it. The other is the cluster. The other is the long-term evaluation of earthquake occurrence. So through the cluster, cluster deformation, seismicity, and slow slip activities. Thank you very much.
P63, P71.
Yeah, good morning, ladies and gentlemen. We have access to a very exciting data set of 10,500 stations deployed in the very eastern Vienna Basin. On the left, you see all the daily activity that we produce, and this allows us great insight into what we usually call ambient noise and what this actually is. And we hope to study this at higher frequencies to get, sadly the movie stopped. On the right, you see Green's functions from ambient noise cross correlations, so wave fields traveling to stations and from stations. And if you're interested in this kind of work and want to learn more about this and see the animations in more detail, please come by my poster. Thank you very much.
P73.
Yeah, good morning. My name is Josephat. So the focus of my poster is on recent seismicity along the Devi Range. This is a southwest extension of the Kenyan Rift Valley. So what I did basically is to develop an empirical relationship between moment magnitude and normal fault parameters. So the results show that the fault parameters range from the fault area 10.9 to 49.1 kilometers squared, and then the stress drop is 0.39 to 1.202 megapascals. So these results show that the fault area is underestimated, and that obviously overestimates the fault rupture area. And so in my conclusion, I recommend fault parameters determined from waveform modeling. So welcome to my poster for more detailed discussion. Thank you.
P80, P88.
Good morning, ladies and gentlemen. Here I'm presenting the results from the area called the Okavango Delta region. The area is located in the northern western part of Botswana. So the past research has shown that the area is technically active, as evidenced by the 6.7 magnitude event. And also the studies in the past show that the area is a terminus of the East African Rift System. And in this poster, I'm going to present the results from the local network that we currently installed, we recently installed in Botswana. So in this way, we are able to detect events in the region more accurately, and we are able to even detect the focal mechanisms of the events in this area. So in this poster, we argue that the area is not clearly a rifting zone, so there is more to be done. So we are invited to my poster. Thank you very much.
P102.
Ladies and gentlemen, I am Martin Bednarik, and this is a stress ellipsoid in my right hand. It could be used as a glyph in a stress map, but the problem is it occupies too much space in order to be readable. With our method, you can squeeze the tensor shape information into the RGB color of a single pixel or voxel. So, this is a stress map made of stress ellipsoids, and this is a stress map made of color voxels. The choice and further applications are up to you. We invite you to our poster to discuss the topic. Thank you for your attention.
P120.
Good morning. We noticed that when surface waves are passing small-scale heterogeneity, they not only bend and are delayed, but they also diffract and interfere, creating a patterns like stripe-like patterns. Similarly, like when light is passing through two slits, which everybody knows from optics. And not only we are now able to measure these things. Here you see the pattern measured like using the measuring arrival angles of surface waves. But we can also invert such a pattern to locate the anomaly which had caused it. And at my poster, you will see the details we were able to infer using the measurement in Europe about a small-scale, low-velocity anomaly which is located in Cameroon under Central Africa. What you see in the central figure, inside that small European region, it's the measurement, and in the background, it's the modeling. Thanks.
P122.
It's the second one. Thank you.
P123.
Hi everyone, I would like to introduce our poster. This is a collaborative project where 10 peaceful nuclear explosions were used to obtain regional velocities in the Siberian platform, Trans-Baikalian block, and the Baikal-Plateau highland. Both the P and S wave calculated velocities match really well with previous models, and we see unique spatial distribution within the area. We see presence of low velocity anomalies both in the crust and underneath the moho. So if you would like to learn more, to talk with me, I would invite you to my poster later today. Thank you.
P124.
My name is Rigo TB from the Sandia National Laboratories. We are going to release several items related to SALSA 3D for the monitoring and seismology community. SALSA 3D stands for Sandia Los Alamos Velocity Model. And we are going to release, the items we are going to release include the SALSA 3D velocity models, the travel time local table computed using those velocity models, and software tool that can be used with this model, which include the geotest software, which is a model parameterization software, PCalc, which is a travel time computation tool, and Loco 3D, which is an event location tool using 3D velocity model. And the poster I'm presenting today with outline where this item are located, what has been released, and what future releases will be. Thank you.
This was the last poster on our list. Thank you.
Yeah, we invite you to visit posters and to see this exciting research which is done. Thank you very much for attending this session. Thank you.
It was interesting. No, it's a very interesting presentation.
No, let's
I
go,
can
please.
imagine
So
that.
I have to get back to another meeting.
And I've got so many things today,
It's okay.
and I must have so I was happy to come into the room anyway later, and then saw my name up here. Yeah, no apologies, but it went very well. Yeah, thank you.
So I think what Thierry said to me was that you were maybe interested in the alpha testers group for the re-engineering. Okay. So for sure, it's not at that stage yet, because we don't have code yet that works that we can test. We only have a framework. And we don't expect anything that works till about next year. But he's now given me your card, so I will send you an email so that we can make. I'm even going to write here. This is about the. I unfortunately don't have my cards with me right now, so I will send you an email, and then I will make sure that we stay in touch, and I can in that way inform you of all the possible options in future, how you can be involved.
From Thierry, I heard that there is a bid, and that will be the deadline is
22nd of July. Is so 22nd of July is the closing date. You can. It's for many different aspects of the software development, not just in engineering, but all the software development that we're using. And you can